Section 3-3, multiplication and division of whole numbers. Now at this point, we already know how to multiply and divide, so our focus is to look at how to model these operations, as well as to understand some of the properties that these operations hold. We can model multiplication of whole numbers using repeated addition. So for a problem like, we have 5 groups of 4 cookies, we can use addition to put the groups together. So at the top of the screen, I have 4 cookies in each group, and I'm adding those groups 5 times because we said we had 5 of those groups. And if we already know how to do addition, then we can solve this new multiplication problem using a tool that we already have. We can use the tools from addition of stacking blocks. So if we're looking at 5 times 4, we can say that's the same thing as adding 4 5 times. And we can also use the number line. 5 times 4 would be like adding 4. So we would put the 4 arrow on the number line, and then we would repeat that 5 times. And we could stack all those arrows together to see that our answer is 20. So first, we can think of multiplication as repeated addition, which is great because if we already understand addition, then this is not really a new challenging idea for us. We're just building on something we've already learned. We can also look at multiplication using the array or area models. So the array model uses intersections of horizontal and vertical lines to count the product. So if we wanted to do 4 times 5, we would start by drawing 4 horizontal lines and then 5 vertical lines. And each of their intersections is part of the total value of the product. And it is simply repeated addition as well because we have 5 dots in the first row, 5 dots in the second row, 5 dots in the third row, 5 dots in the fourth row. So we're really doing 5 plus 5 plus 5 plus 5. Or we have 4 dots in the first column, another 4 in the second column, 4 more in the third, 4 more in the fourth, and finally 4 dots in the fifth column. So that again looks like 4 plus 4 plus 4 plus 4 plus 4. So we can use these tools to help solidify the idea of multiplication using the number line, using the blocks, using the array, or the area model. Area model looks a lot like the array, but instead of counting intersections, you make complete squares and you count each one of the squares. Now, that being said, these two models are so similar, it's easy to accidentally confuse the two and draw the area model, and instead of counting the squares, you start counting the intersections. You would get that problem wrong because you're not using either of the models correctly. You're kind of mashing up the two in an incorrect way. So with the array model, you're counting intersections. And with the area model, you're counting squares. Now the array model can actually be really fun to demonstrate products of numbers that are more than just single digits. And we'll see a little bit of that later. We can also look at the Cartesian product model. We've talked about Cartesian products before when we learned about set operations in Chapter 2. So let's take a look at how to use the Cartesian product model to represent multiplication. In this scenario, we're taking 2 courses, and you have to pick what you would like to take in each course. For example, you can take world history, or you can take ancient history as your first course, and your second course, you can take Latin, French, or German. To represent all the possible combinations that we can take, we can use a tree diagram. This tree diagram represents our class schedule, and we have our 2 choices for the first class, either world history or ancient history. After we've made our decision for our first course, we then have to pick from 3 language courses. either Latin, German, or French. And notice it doesn't matter what we picked for our first course. If we picked world history or ancient history, we still have the 3 language courses to choose from for our second course. And then to read our tree diagram, we'll just follow one of the branches. For example, maybe we chose world history for our first course and French for our second course. Our schedule would be world history and French. So all of the different possibilities that we could come out with would be listed at the end after we've read through every branch on our diagram. We've talked about the fundamental counting principle as well, and we can use that here to help us figure out just how many choices we really have. We know that our first course has 2 choices. Our second course, we have 3 choices. So the number of ways event 1 can happen is 2. The number of ways event 2 can happen is 3. We multiply those together to see that there are 6 possible outcomes, and we're able to see each of those 6 outcomes in our tree diagram. Now, there's some properties that we want to talk about for multiplication. And in mathematics, whenever we define an operation like addition or multiplication, we like to list the properties that those operations hold. One of the properties that's not often discussed in lower level mathematics is the idea of closure. And it's a pretty abstract idea, so let me try to simplify it. If an operation is closed on a set of numbers, for example, we're dealing with whole numbers. And whole numbers are the numbers that start at 0 and are positive numbers counting up. And they go on forever. So the set of whole numbers includes 0 as well as all of the counting numbers, 1, 2, 3, 4, etc. So if I wanted to explain closure of multiplication on the set of whole numbers, what that means is that I can pick any 2 whole numbers from the set, and if I multiply them, the result is a number in the whole numbers set. Basically, what this means is that I can't take 2 whole numbers, multiply them together, and get a fraction. Fractions aren't part of the set of whole numbers, so we wouldn't expect that to happen. Multiplication is closed on the whole numbers because we are allowed to pick any 2 whole numbers we want, and when we multiply them together, we're guaranteed to get another whole number as our product. Multiplication in whole numbers is also commutative. That means that I can multiply in any order that I want, and the value of that product is not going to change. So 5 times 3 is the same thing as 3 times 5. This happens in a lot of operations, but it's not guaranteed on every operation in mathematics, so it's a good thing to state when it is true. The associative property says that I can multiply in whatever pairs I want. For example, if I multiply 5 times 3 times 7, well, technically, I can only multiply 2 numbers at a time. I can't multiply 5, 3, and 7 all at once. We don't know how to do that. Multiplication happens between 2 numbers at a time, not 3. So I could multiply 5 times 3 first, and then the result of that times 7. Or I could multiply the 3 and the 7 first, and the result of that times 5. Either way we do it, we get the same result. So the associative property says that we can move these parentheses wherever we want, and the result will be the same because multiplication is associative on the whole numbers. Next we have the identity. The identity is a special number in a set that when you apply an operation using that number, you don't get any change. For example, multiplication, the identity is 1. Because no matter what I put inside of this box, When I multiply it by 1, the same thing comes out. For example, if I put a 3 in this box, 1 times 3 is still 3. If I had put an 11 in this box, 1 times 11 is still 11. So we call 1 the identity because it doesn't matter what we multiply 1 by, it comes out unchanged. Even 0. 1 times 0 is 0. So 1 is the identity of multiplication. And then we have one more property, the multiplication property of 0. Multiplying by 0 will always result in a 0 no matter what you're multiplying 0 by. So it's kind of similar to multiplying by 1, but it's not the same. 0 times anything in this box will always come out to be 0. It does not matter what I put in there, the result will always be 0. Let's do some examples here. Let's use an area model to show that the product that we have on the screen, so x plus y times z plus w, is equal to x times z plus x times w plus y times z plus y times w. Now, if we were to do the array model or the area model, what we need to do is represent each of these numbers with some area. So x plus y, I'll represent that on this vertical line that I've drawn. X and y are two separate numbers, so let's separate this to say maybe this portion is x, and the remainder of this vertical line is y. And then we need to do the same thing for the z plus w, so I'll draw a horizontal line that represents z plus w. And again, z and w are two separate numbers, so I'm going to break them down into two pieces. So maybe this portion is z, this portion is w. Then when we complete the area model, we can look at this as the area of 4 smaller squares. The area in this top left square has one side that is length x, one side that is length z. And we know that area equals length times width. So if we call x the length, z the width, the area of this first square looks like x times z. But we have 3 other squares. What about the one below that? So on the bottom left, we have y as our length, z as our width. That looks like yz. Top right, we have another rectangle that looks like x times w for the area. And then bottom right, we have y times w. We have these 4 smaller rectangles inside of this larger rectangle. So to get the area of the larger rectangle, we would need to add all 4 areas from the smaller rectangles. That would look like x times z plus xw plus yz plus yw, which is exactly what we have at the top of the screen. We can use the distributive property over multiplication to justify that same result. So often we hear of FOIL when we talk about distributing. FOIL is very specific to a binomial times another binomial. Remember that bi means 2. So in this first group of parentheses, I have 2 numbers. We call that a binomial. And same for the second group of parentheses, we have 2 terms in here, so that's a binomial. FOIL tells you to multiply each of the possible pairs in a certain order. So F stands for first, O stands for outer, I is inner, and L is last. So multiplying our first terms, the first terms in each of the 2 binomials, x and z. Then we multiply the outer terms. X is on the outside, so is w, so our next term is x times w. I stands for the inner terms, y and z are on the inside, so that's our next term. And then our last terms. Y is the last term in the first group, W is the last term in the second group, so Y times W. So we can use our area model to justify this result, or we can use the distributive property to show that multiplication distributes over addition, not division. Typo there. If we wanted to do this step by step, we could break open the first set of parentheses. Instead of using FOIL, we could distribute first x plus y times the second group. So that would look like x times the second group plus y times the second group. And then from here we distribute the product into the sum. So x times the sum of z plus w would be xz plus xw. And then we would distribute the product y over the sum z plus w to get yz plus yw. So there's many ways to get to the end result. Here's an example of proving closure. So here we're looking at the operation of multiplication, and we're looking at the set of whole numbers. So the set A is the product of 6 multiplied to the number n, where n is a whole number. We want to show that this operation is closed under addition, meaning I can pick any number that lives in this set, and if I perform this operation, I would be able to see a number that belongs in that set. So the first thing that maybe we want to do is think about what elements live inside of this set. Remember that if n is a whole number, then n is either any one of the numbers, 0, 1, 2, 3, 4, 5, 6, etc. So A has numbers that look like 6 times 0, 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, 6 times 7, etc. Oh, I forgot 6 times 6. Now, I've written these out after I've already multiplied them, but maybe we write them out as actual products. 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, 6 times 6, 6 times 7. Oh, and it continues. So let's use the ellipses to say that these sets are not finite. They're infinite, in fact. So now that we know what the elements of A look like, they look like the numbers we have here on the screen, we can talk about whether or not they are closed under addition. So we're doing 6 times n using whole numbers, and I want to pick any two numbers from the set A. I could pick something like 6 times 3 and 6 times 7, or we could get more general and we could say 6 times any whole number, like 6 times j, and 6 times k, where j and k are also elements of the whole number sets. And maybe I call 6 times j A, and I call 6 times k B. Then what we want to show is that if we add the two numbers that we took from the set, that we will get a number that belongs to the set. So A plus B would look like 6j plus 6k. And we're going to use the distributive property to reverse distribute the 6, so that we have 6 times j plus k. Now we know that j plus k, two whole numbers, when they're added together, they're equal to another whole number, which means the form that we have looks like 6 times a whole number. Well, 6 times a whole number, that is literally the definition of the elements that belong in A. So that means this is also an element of the set A. So what we did was took two numbers from the set A, added them together, and then we used some mathematical reasoning to arrive at the conclusion that the result is also an element of A, which demonstrates closure. Now let's talk about division and modeling division. One way to model division is to use a set partition. For example, if we have 18 cookies and we want to give an equal number of cookies to each of three friends, let's say we're talking about Bob, Dean, and Charlie, we want to divvy up these cookies, and we could do that one at a time. Give one cookie to Bob, give one cookie to Dean, give one cookie to Charlie, and then we can continue distributing cookies one at a time until we run out. This is a partition where we're taking a group and breaking it into smaller parts, specifically equal smaller parts. We're not giving Bob 2 cookies and Dean 1 cookie and Charlie 5 cookies. It's one at a time. Once we've run out of cookies to distribute, we can see the partition. Each group has to have 6 cookies in it. So one way to represent division is to do a set partition. Now, of course, this is not the most efficient way to calculate division. It's a way to teach it so that we understand what it means to divide. Another way to teach division is to talk about it in terms of a missing factor. So if we are still talking about the same scenario, 18 cookies, and we want to distribute the cookies to 3 friends evenly, what we need to do is think of a number that if we gave each friend that number of cookies, the total number of cookies would be 18. So maybe we try guess and check. Give each person 3 cookies. Then that would look like 3 plus 3 plus 3, or 3 times 3. This is the idea of missing factor. So we do 3 times. I'm going to use a dot to represent multiplication. We don't know what goes in this box. We're guessing and checking along the way. So if we had guessed 3, we would say that this is not a true statement because 3 times 3 is not equal to 18. So that's probably not the right answer. So instead of giving up, we use our guess to make a better guess. We know 3 times 3 is 9, and that's too small. So we probably need to give everybody more cookies, not fewer cookies. So maybe we try 5. If each person gets 5 cookies, that would look like 3 times 5. But 3 times 5 is 15, and 15 is not equal to 18. So again, not a good enough guess. And notice that we're still undershooting it. What if we tried a bigger number, like 10? Well, 3 times 10 is 30, and that's too big. So maybe 10 cookies isn't the right answer either. Maybe we try 6 cookies. 3 times 6, that is 18. So it's definitely 6 cookies to each friend, and we figured that out by using the missing factor model. We can also use repeated subtraction, which looks a lot like the partition model, but instead we're looking at it as subtracting a group of 3 on each go. So we've got 18 cookies. We have 3 friends. So if we think about giving each person 1 cookie at a time, that takes a lot longer than saying, hand out 1 cookie to everybody. So we take 3 cookies and give 1 to each person, meaning we've subtracted 3 once. We do it again. We subtracted 3 twice. Do it again. We've subtracted 3 times now. 1 more, that's subtracting 3 4 times. Another one, we just subtracted 3 for a 5th time. One last subtraction of 3, and we can see that we have subtracted 3 a total of 6 times, and it was necessary to do subtraction of 3 6 times to run out of cookies. So removing a group of 3 a total of 6 times, that's another way to represent division. And we get the same answer. In context, each person still gets 6 cookies. So we just solved one division problem 3 different ways. Speaking of division, let's take a moment to talk about something called the division algorithm. Any two numbers, a and b, where b is not equal to 0, there's going to exist unique whole numbers, the quotient and the remainder for a and b. The division algorithm says the number a is equal to the product of the number b and a quotient from a and b, plus possibly some remainder. And if we're dividing, for example, a divided by b, if we're dividing by b, the remainder has to be smaller than b. And we don't talk about negative remainders, so the remainder also has to be greater than or equal to 0. Notice the remainder cannot be equal to b. If it were, then we would just be able to remove one more group of the size b. So for any problem a divided by b, we could rewrite that division problem using this division algorithm equation, and that can help us solve more complex problems. We will do a lot of division algorithm ideas in Chapter 4, but for now, let's just try a small problem using the division algorithm. In this problem, we're told that 123 is divided by a number, and it's a mystery number. We don't know what it is. However, we do know that the remainder is 13. So if we think about 123 divided by some mystery number b, we know that we can rewrite that as 123 equals b times a quotient plus the remainder, which we're told is 13. We also know that the remainder has to be smaller than b. And it's already greater than or equal to 0, so we don't have to bother stating it, but why not? Our goal here is to find out what the possible divisors are, meaning, what is b? Can we find out what number b is, so that when we divide 123 by that number, we get a remainder of 13? And maybe it feels like it's not possible to answer this problem, but I guarantee you it is. And all we need to do is work with this division algorithm expression that we built to solve for b. We can start first by subtracting by 13 on both sides, so that we have 123 minus 13, or 110, is equal to the product b times q. We don't know what b or q are. However, we do know that they're whole numbers and that when we multiply them together, we get 110. So essentially, we just need to factor 110 and find all the possible factors. We could do 1 times 110. We could do 2 times 55. We could do 5 times 22, or we could do 10 times 11. Now, if we're looking at the divisors, again, we're looking for b. We want to know what the possible divisors are. That's the b value in this division algorithm. We know that b has to be larger than 13. So b cannot be the 1, but it could be the 110. It couldn't be the 2, but it could be the 55. It can't be the 5, but it could be the 22. And if we look at 10 and 11, neither one of those are larger than 13. Although those two whole numbers do multiply to be 110, they don't work out because of the value of b. For example, if we had tried 123 divided by 10, you would get 12 with a remainder of 3, because 10 times 12 is 120 plus the remainder of 3. So because we know that the remainder was 13, we can eliminate the numbers 10 and 12 from our list completely as possible divisors. So the only possible divisors that we could have for this problem are 110, 55, or 22. We talked about multiplying by 0 and 1, but now let's talk about division. Dividing by 1 has no effect on a number, and we could justify that using the missing factor idea. So take any number you want, like maybe 7, and divide it by 1, and you could say, what is the answer to that? Well, we could rewrite this as a missing factor problem, where we say 1 times some number needs to be equal to 7. Using the multiplication identity that we have, 1 times 7 has to equal 7. Therefore, 7 divided by 1 has to be 7 as well. Dividing by 1 results in the same number you started with. So just like multiplication, multiplying by 1, dividing by 1, they don't change the value of the number you're applying the operation to. But 0 is a little more tricky. So if we have two numbers multiplied together and the result is 0, we can make a few assumptions. Either this first number is 0 and the second number is whatever you want, or the second number is 0 and the first number is whatever you want. Think of like 11 times 0. Or maybe both numbers are 0. So with multiplication, we know how 0 works. We also know that division and multiplication are related through that division algorithm. If we don't have a remainder at all, that says that division of A divided by B, it's actually a product. So they're closely related. If we don't know what Q is when we divide A by B to get the quotient, we could rewrite our division problem as this product using the division algorithm, and we use this missing factor idea. So A is equal to B, which is a number that we're supposed to know, times the quotient. So if we take our division problems that involve 0 and we try to rewrite it using this division algorithm, we'll see what happens. 3 divided by 0, that's like A divided by B. That would look like 3 equals 0 times Q. Well, we know 0 times anything is 0, but this expression is saying 3 is equal to 0, and we know that's not true, which means dividing by 0 is a problem. In fact, we can generalize that whole first problem and say any number A divided by 0 will be undefined because we can't find a product of 0 times a quotient that would give us A back. So A divided by 0 would look like A equals 0 times a quotient, and unless A was 0 itself, this will never work. Let's take a look at this next one, 0 divided by 3. If we wrote this using the division algorithm, that would look like 0 equals 3 times a quotient. And in this case, we can pick the quotient to be 0 so that we have 3 times 0, or 0 equals 0. So this one's fine. Dividing by 0, that's the problem. 0 divided by 3, not a problem at all. And what about 0 divided by 0? If we tried to write this using the division algorithm, it would look like 0 is equal to 0 times a quotient. And the problem with this is that I could plug in any number I want for Q, and it will always be true. So there's too many solutions to this problem. It's also undefined. So out of all three of these problems, these two are undefined. The last thing we have to talk about is order of operations. In chapter 3 so far, we've talked about addition, subtraction, multiplication, and division, which means we have pretty much enough for a foundation to talk about multiple operations happening on one expression. Now there's two ideas that are pretty big for order of operations. One of them is PEMDAS. This tells you the order that we should work on is parentheses first, then exponents, multiplication and division, addition and subtraction. We also have GEMMA. GEMMA says grouping symbols first, exponential operations next, multiplicative, let's pause there for a second, multiplicative, that means more than just multiplying. Because division can be written as a product using the division algorithm, multiplicative operations includes both multiplication and division. And then lastly, for GEMMA, we have additive operations. And addition with negative numbers is the same thing as subtraction. So we can write additive operations, and that includes both addition and subtraction. You might like GEMMA better because it only has 4 things to do on the list, and who doesn't love a short to-do list? But one of the real reasons why GEMMA has more power is because it doesn't mislead you when it comes to these two operations. In the PEMDAS order of operations, it looks like you should do multiplication before you do division, but that's not always true. It also looks like you should always add before you subtract, but that's not always true either. These two operations, multiplication and division, they are the multiplicative operations, and we need to perform them left to right, the same way that we read sentences, left to right. Same with addition and subtraction. Those two operations are the additive operations, and those need to be performed left to right. So PEMDAS is powerful, but it can be confusing if you forget multiplication and division are actually grouped together. They don't look grouped together in that list, they look separate, like you do them first multiply, then divide. But the reality is you do them interchangeably depending on who appears first. Another reason why GEMMA is powerful is because inside of the PEMDAS operation list, I don't see anything about radicals. But in this expression, root 48 plus 1, that's a grouping symbol. That says I need to do this operation underneath the radical before I do anything else. Also, this rational expression, which has multiplication, division, and subtraction, nothing in here talks about fractions. PEMDAS doesn't talk about that. However, a grouping symbol, that's exactly what this large division bar is grouping. It's separating a numerator and a denominator. We could write the same problem as 36 minus 3 times 4 divided by 15 minus 9 divided by 3. And in this notation, I am using parentheses, so PEMDAS would be fine here. But when it's written without the parentheses, using the large division bar, it's sometimes overlooked that there's grouping happening. But there is grouping, and we would need to simplify the numerator, then simplify the denominator, and divide last. This problem, we see that there are multiple operations happening, and in fact, the way that I like to explain order of operations is that we need to first look at the terms. Terms are separated by addition and subtraction. So looking at the big picture, this thing is separated from this thing because there's subtraction here. So we have two terms. Within each term, we will have factors. Factors are things that are multiplied together. So we have 2 factors here, 3 times 8, but those are within parentheses. So division is separating the factor 150 and the factor inside of these parentheses. Remember that division is a multiplicative operation, so that does help us see the separate factors because there's a division symbol. And then inside of this big parentheses factor, we can see that we have two terms. We have the 6 and then the 3 times 8, and then 3 times 8 each has a factor. Once we have that, we can start to slowly break down our problem. So first we just digest the separate terms and then we work our way into the smallest piece. So we can see inside of the parentheses is the first thing that we need to work on. 6 plus 3 times 8. Now if we multiply our factors, 3 times 8, we get 24. So in our parentheses, we're really looking at 6 plus 24. And then we can add 6 and 24 to get 30. So inside of this first green parentheses set, we just simplified that down to 30. We simplified that factor completely. Now we can rewrite it to say 150 divided by 30 minus 5. And then 150 divided by 30, we need to do our multiplicative operations before we do our additive operations. So 150 divided by 30 is 5. And then we bring down our additive operation. 5 minus 5 will get 0. I have one last problem that I want to work through using order of operations, and that is the one you see on the screen. And this problem really highlights the shortcomings of PEMDAS. Let's say you learned PEMDAS years ago, but you haven't used it in a while, and so when you look at PEMDAS, you forget that multiplication and division happen in the same step. Sure doesn't look like it when it is written out: multiplication, division, addition, subtraction. So if we look at our expression here, we say, oh, parentheses first. Okay, 1 plus 2, that simplifies to 3. So we have 6 divided by 2 times 3. Then we read our PEMDAS operations. There's no exponents. There is multiplication. Let's go ahead and do that. 2 times 3 is 6. So we have 6 divided by 6 now. And then after multiplication is done, we move on to division. 6 divided by 6 is 1. But guess what? That is wrong. It's wrong because you don't do multiplication before you do division always. You only do multiplication first if it appears first on the list. If we go back to this step, everything we did before this was fine. But if we look more carefully, 6 divided by 2 times 3, division and multiplication are both multiplicative operations, which means we need to do them all in the same step in order from left to right, the same way that we read sentences. You wouldn't read operations multiplicative, you read multiplicative operations. So we go left to right, which means we need to divide 6 divided by 2 first. Then we can multiply that result by 3. The real answer is 9. You've probably seen problems like this on the internet, Facebook, Instagram, Twitter, whatever. These types of problems have gone viral because this is a tiny mistake that many people make because they learned PEMDAS, but they tuned out or they forgot about multiplication and division happening in the same step where you apply them from left to right. So Gemma doesn't make that mistake because it simply says multiplicative operations, not multiplication, multiplicative operations, which incorporates division. So that one word does mean both the operations of multiplication and division.